Welcome back, everyone, to day 3 of the Cybersecurity with Python and the Microbit Workshop. This is day 3 of 3, April 26th. Here is a link to this slideshow, which has many important links in it that I'll be following and that you might find to be useful later on. Chat. Paste. Okay. Reminder that you can wave your mouse around, click the view button, select exit full screen, and tile the windows side by side if you have a single monitor and need some extra real estate. Today we'll be finishing up brute force, then taking a look at malformed packet attacks, educator resources, cyberbot robot demos, resources in general, and upcoming workshops, purchasing, and then after we stop recording, we'll have some questions and answers. So I think we left off with the brute force attack example of a binary attack. Oh, that's right, I'm sorry. So we have to, first of all, make sure that everybody who is so inclined has their microbit modules connected each to an individual editor tab. And let me adjust the focus here. There, how's that look? A little bit better? All right. Okay, so then if I usually just give it a try first off, see if it works. And again, it's something that we only do really during this workshop because we need to have 2 microbits on a network in air quotes, and so normally students connect a microbit to a computer, and you have another student with another microbit on the computer, and then several more, and they're all part of that microbit network. So what we do is we click the 3 dots next to send to microbit and select connect, and then choose a instance, and I'm choosing the one that ends in 3000 first. And then I'm going to the next editor, clicking the 3 dots again, selecting the 3 dots again, and then in my case, there's a second serial number ending in 5000, and so I'm clicking connect on that. And now need to go back. And this is similar to the scripts that I emailed you. Okay, so now we know that the darker blue trimmed microbit on the left is microbit A. And then it's actually more of a greenish color. I think the white balance is a little off here. This is almost green, a little bit turquoise. And now this one is microbit B. So anytime I load a script with this computer, it's going to go to microbit A. Anytime I load a script with, or pardon me, anytime I load a script with this tab, it's going to go to microbit A since they're connected. And then anytime I load a script with the second tab, it's going to go to microbit B since they're connected. And the browser, so long as these guys are connected and the browser stays open, it will remember that setting. So moving on to the decimal version. So this is a next, well, I guess really I should probably restart from the beginning here. So we'll get our bank vault going again. So what I'd like you all to do is get your transmitter and receiver scripts going. Here is the page. So you'll be putting your transmitter presumably into A and then your receiver into B. And then we'll just make sure that it is that the basic ability to enter a PIN and gain access to the other microbit is working. Okay. I meant to do that, or well, okay, I made a little mistake here. I meant to have microbit B be the one that's the vault, the one on the right. And then microbit A is my pin pad, my radio pin pad. Copy. Okay, so the one with the dot in the center is the vault locking mechanism, what have you. And then the one with the light in the center rather, and then the one with the light in the bottom left, that's actually showing that the first digit of the pin is 1. And so again, if I press the A button, I can toggle between 1 and 0. And the correct combo is 0, 1, 1. And I'll go ahead and send it 1, 0, 1. And access is denied. Then if I, since it starts at 0, I can just advance to the next digit and then change that to 1 and advance to the next digit and then advance one more time because this is 0, 1, 1. And now we have access granted. And since we have 3 binary digits, there are, as the text introduces, there are 2 to the 3rd or 8 different combinations. And here they are. Now moving on to how those kind of things are attacked. I know that I went over this on the tail end of Friday, but it was a little bit hurried. So I'm just restarting with the very beginning of brute force. So this script, you'd want to replace what you have in your pin pad so that the microbit that you loaded the script to be the pin pad is the one that you want to load the bank vault crack script into. And I'll go ahead and paste that into the chat and you can go and grab that and replace it. And then we'll watch it go to work with a brute force attack. So I had my left tab being the one that is the pin pad transmitter. And so I'm going to paste the oopsie. I thought I was going to paste the bank vault crack script over it. There we go. Okay. And when I load that, when a student loads that, they'll see an arrow pointing to the A button. Now, before we start that, let's take a look at the serial monitor. And in fact, I want to, there's 3 dots in the separator between the serial monitor and the editor pane. And so I'm going to drag the serial monitor pane up a little bit before hitting the A button. 0 access denied. And so it's going to go through all the different combinations. And it found out that 011 is the correct combination. And so there is a brute force attack for you. And we start with a very limited pool of combinations. So next up, we'll do the same thing with a decimal vault. And it's the same kind of grab the transmitter and put it in one editor and grab the receiver and put it in another editor and load both the scripts. And so we just want to test out, and I'll show you how this works. So I have to go and grab the transmitter. And then the receiver. And now here's our vault, and then here's our pin pad. And the way the pin pad works now is that you have to hit the A button, and you can count from 0 up to 5. So if I do 4, 3, 2, my access is denied. And I need to remind myself it's actually 3, 2, 4. And that's the one that should get us in. So 1, 2, 3, enter. 1, 2, enter. 1, 2, 3, 4, enter. And there we go. Now, the brute force attack for that is one that we don't want to wait through. It's long enough for students to get fidgety, but too long for trying to keep a well, it's too long for trying to get through all the material we've got. So I'll basically show you what happens. Basically, here we can see that it's going through the different combinations. And when it gets to 3, 2, 4, eventually access is granted. And so this is what it looks like. Or this is similar to what it looks like in your serial monitor if you run the code on this page. And you know what you can do is you can run that and wait and see if I don't end up calling you away to another sample script. So this is the bank vault cracking code right here. And I just pasted the web address in. Ciphers can also be cracked with brute force, especially encryption keys on disk drives, or now that they're solid state, those are things that can be brute force attacked with large computers fairly efficiently. And with this, it's talking about how an attacker might make an educated guess that we're using the Caesar cipher. And the Caesar cipher certainly has more combinations than the then 3 digits each with 6 options, or then 3 digits. 3 digits with 2 options is the fewest combinations. 3 digits with 6 options gave us more combinations. And now we have, well, really there's 26 different combinations you can use here. For trying to use a Caesar cipher to examine encrypted information. And so this is where we used the share a smile, share an angry, and share a sad emoji earlier. And so for this, we'll have to go back to the share something personal activity and get that one going again first. And so we have our transmitter and our receiver here, so we'll get those started. And just make sure that we've got the one transmitting to the other. Okay, so I want to send you the address. Okay, so there's the page to try that out. And sorry if I went too quickly and you didn't have time to see the decimal vault crack get to its completion. We'll have a 5-minute break at the top of the hour. Anybody who wants to try that can do it then. Okay, so here we are doing send images. And then the receive images. Okay, so what we have here is microbit A is sending a series of smile, frown, and glower. And it's showing, so this script is showing, this is the transmitter script, and it's showing what the encrypted version of each one looks like given an encryption key of 3. Oh, sorry, hold on. Okay, so now I'm in the transmitter, and it's displaying in the serial monitor, so you can use your show serial, hide serial button to bring up what the transmitter is transmitting. And we can see that basically we see the encrypted value and the unencrypted value. But as a receiver of unencrypted data, you would, not knowing the key, you would just see, VDG and DQJUB and KDSSB over and over again. And so one way to do this is to say, all right, if we make an educated guess that it's a Caesar cipher, what can we do to figure out what the key is? And the answer, brute force wise, would be to simply go through and try all the different keys, decrypting them one at a time, and see if there's any intelligible information therein. And to do that, first of all, the script needs to be modified so that it doesn't. I don't know if you remember on Wednesday, but when we started sending encrypted and the sniffer was trying to check for unencrypted data, it actually crashed its application. And so this is a little activity on preventing that. And then, so this was back in share something personal and sniffing attacks and defenses. And now we are in brute force attacks and defenses. And so this is the script that is used to, better just paste you the text. This is the script that is used to run a brute force attack on that communication and figure out the so we'll take the receiver and try running the brute force attack script. Why isn't that doing what I want it to? Okay, I did something wrong. Oh, okay. So this is the transmitter script that I grabbed. Sorry. So the receiver script is the one that you want to run. This should be a brute force attack. So, and let's see, crack cipher with brute force. Yeah, so the most recent page that I texted you should be the one that runs the brute force attack. And hopefully I grabbed the right script this time. Yeah, here we go. And as we look at this, here's the encrypted value. And so one of the things that are done when trying to figure out if we stumbled across a decryption key is to take a look at each of these different combinations. And lo and behold, combination number 3 is intelligible and even fits our application. And so by taking some data and then going through and trying each of the encryption keys that's available to a Caesar cipher, and there are 26 of them, we were able to pretty quickly figure out what the encryption key is, and that would allow a brute force attacker to join in on this particular microbit conversation. The chapter then goes on to talk about how you can increase the number of combinations. And basically it provided examples of, hey, here we have a really weak cipher, here we have a stronger one, and then here we have an even stronger one. And each time it takes longer to break the combination. But so here is an example where the cipher has 26 factorial different options, which is a very large number. And it's called the scrambled alphabet cipher. And it's something that I just wanted to bring your attention to, that the chapter goes into making stronger and stronger ciphers. And that includes generating a custom cryptobit. So if you don't want to scramble up all the letters in the alphabet, which is kind of a pain, might take a pencil and paper or a text editor and starting with the alphabet and moving the characters all around. There's a script that does that, and it's kind of fun. I'll go ahead and have you try this one out. So the script went through and kept on randomly selecting characters, and eventually settling on this cryptobit as the randomly generated one. You can, I believe that you can change the random seed, because this is a pseudo random thing. I don't remember now exactly how good the random is. Typically, let's try setting this to 1, or let's try rerunning it and see if, okay, copy. I'm gonna just paste this into the chat and then try again. If we run this again, let's see if we come up with the same cryptobit because it's pseudo random, or if there's some extra smarts in the random number generation that the microbit uses. Okay. That actually is different. So that's nice. And then it goes on to talk about strengthening previous applications. This one has to do with the velocities of a keyboard-controlled cyberbot robot. And that is where we stop on the brute force attacks. And then we move on to malformed packets. And let's see here. So here's a revisit to our distributed countdown timer, or our radio controlled countdown timer. And this one is kind of interesting because it has, you could consider it malicious software, since the transmitter has a built-in way of disabling the receiver. So instead of counting down and displaying a message, the receiver will end up throwing an exception, and it won't continue to work as it's programmed to until you restart it manually. And so we'll have you try out. I'll have you try this out, and I'll also demonstrate paste how it should look. So this is pretty much the same countdown receiver that we used earlier. And it has no exception handling, which is a critical weakness. I managed to demonstrate that it received data from the send a smile frown glower, and that was enough to crash it. So the way the test works is that we want to simply start by operating the remote controlled countdown timer the same way we did previously. And after that, try sending -1 to it. And then the countdown timer will no longer work. So as we do that, make sure I'm in the sender. Yeah, this is the sender. Oh, no, it's the receiver. Okay, now let's try this. Okay, so enter the countdown start, 3, lift off. And that worked. So we'll just run it again to show that it can be used repeatedly. Okay, then we can try -1. That's our little backdoor to send a malformed packet in this particular script. And the message can be anything. And now this microbit, the receiver microbit, is not going to do anything until I go and press and release the reset button to restart it. It's currently displaying an error message in its 5x5 LED matrix display. And so in order to get it to work as a countdown timer again, we have to either reload the script or press and release the button at the very least. And now that I've done that, I can go back and continue to operate it. And it's still ready to receive the next thing. So here's an example of an attack script that has this little backdoor basically saying if the value is -1, then what happens is that this script chokes on that -1. And I want to say that it also, yeah, pardon me, it does not give it -1. What it does is it goes into the dictionary and replaces the number -1 with some text. And so since text and numbers just don't work together in subtraction, that's what causes the exception to occur in the receiver microbit. So how to fix that? exception handling, exception handling, exception handling. And this is one where it's up to the student to manually modify the script. So let me see if I can modify that and then paste it to you. Maybe too large. Okay, so here is the receiver script. And here are the modifications. So above while value is greater than equal to 0, we want to add try. Then this whole routine right here, the while statement and all its substatements needs to be indented. The quickest way to indent something in a Python editor is to simply shade it and then hit the tab key. That will indent it. Then it's asking to have an except added, and this exception handling, I think, was introduced. Yeah, it was introduced on day 1. And there's a whole chapter on it. And since we're just kind of doing a little bit of show and tell at this point, don't worry if you don't feel confident with the nitty-gritty details of exception handling. That'll come after going through the textbook, the online textbook. Again, to indent it, I'm shading and then hitting the tab key. And this will probably fit in the chat. I guess I'd better make sure first that it works. Okay, -1. So notice that it displays an exception message. But did it stop in its tracks, or was that prevented? Yes, it did not stop in, or no, it did not stop in its tracks. Yes, the exception was prevented. And that is an example of basically students learning that they really need to use exception handling when they don't know what kind of data is going to be coming down the pipe. And let's see, did I paste that into you already? Looks like not. All right, so here is the modified receiver code. I'd like you to try that for yourself. And then go ahead and give me a thumbs up when you were able to verify that it works with regular numbers. Thank you, Kevin, for the thumbs up. And then does not crash when you send it -1. Excellent, Raymond. Elisa, very good. I didn't expect you guys to be so fast. Heaven knows I wouldn't do it this quickly if I were on the other end of the Zoom. Nilu, or Nilu's grad student. Good job. All righty, give me a shout to slow me down if I'm barreling ahead too quickly here. Next up in malformed packets is, again, sharing something personal, but the script is changed up a little bit. I kind of wanted something cooler here. So here is the emoji send, and we're using buttons to send the emoji this time. And again, this is malware. It has built-in stuff that will disable the receiver. Let me see if I can paste that through to you. Oops. Oh, pardon me. So this is the same for the transmitter and receiver. So that script that I just pasted in is for both microbit Python editors. Now, this one is a LED matrix display version. And you can basically send it one of, can't remember if it's 3 or 4 different emoji. We've got the image yes is a check mark, image no is an X, image heart is a heart, and then image skull is the one that if you choose that, it's going to crash your receiver because it's going to send data that the receiver's not ready for. It's a packet that's not properly formed for the receiver. It's a malformed packet, and it's going to disable the receiver microbit. So going to, and actually you can do this with either one because these are both transmitter receivers. So I can, for example, send an X from microbit A to microbit B, selecting with the A button and then pressing the B button to send. And as soon as I press the B button, it updates on the receiver microbit. I can go to the receiver microbit and advance it one more and send a heart to the formerly transmitter, now receiver microbit A. Going back to microbit A, if we advance one more, now there's a skull. It's a little bit difficult to see, but that is a skull emoji. And when I hit send there, we get the frowny face and then an exception message that on line 33, there was a problem. And then we can see more about what that problem was in the so it did not send image.yes, image.no, image.hard or anything like that. What did it send? So if the image is skull, instead of sending the emoji like image.yes, image.no, etc., what it did is it replaced that with the text malformed packet. And when the receiver went, and by the way, this is all talked about in the in the chapter. So I'm just telling you things that are being talked about in the chapter, and in the interest of saving time. And so basically it choked on this line because it was not able to run up and find the image up in its list, because instead of receiving a number within the list, and remember I talked about lists on Monday, so this is a list. It's contained with square brackets, and this is a list of text text that ends up becoming an object like image.heart or image.skull on line 33. Or rather, 33 grabs the image or grabs the text, and then 34 takes that text and changes the string into the executable image.yes or image.no. And then display.show of image becomes display.show of image.yes or image.no, something that display.show can actually do something with. And as for how to fix that, again, we're not going to let the students copy and paste everything. So here is the solution. No, this is adding encryption. Prevent freezing. So basically we do two levels of protection. We first prevent the freeze, then we add the encryption on top of it. And so to prevent the freeze, here we go. And remember that to indent multiple lines in the Python editor, you can simply shade them and hit the tab key. And what it does is it then goes to the most recently displayed image after flashing a sad face on and off several times. Okay, so let's see if this works. And if it does, I'll go ahead and send you the corrected script. Okay, so I'll send an X, yay, the everything's working normally. And I'm gonna skip sending the, or actually, no, let's go ahead and send the skull. Okay, let's try it. Maybe I did it on the, okay, so that does crash it going the one direction. Ah, that's right. Okay, so I'm going to press and release the reset button to restart the microbit I crashed. And I'll press and release the reset button of this one too. Okay, so now we're starting over again. If I send an X or an X, great. And if I send a skull, it flashes a frowny face and then goes back to the X. So if I send a check mark and then go and send a skull, it goes back to the check mark that it previously had. And so now it is gracefully recovering from receiving malformed data. Now, another aspect of malformed data is it's usually sent in a barrage, but that is covered under DOS attacks, which I have not done a unit on that yet. It's kind of difficult to really recover from a radio noise barrage on a microbit, so I've been trying to figure out a way to gracefully do that. And frequency hopping code is a little bit tricky. So that is one way to run away from a transmitter sending a barrage of malformed packets, but it's something that it's difficult to get multiple microbits on a network to all cooperate to jump between one frequency and the next to avoid that kind of noise. Keyboard control of the Cyberbot. I'll just talk about this one a little bit. Basically, just a reminder on how keyboard control with the Cyberbot works is we're using a terminal to control and orchestrate the motion of one or more Cyberbot. And by terminal, I mean the serial monitor. So that's one microbit connected to the computer, and then a whole bunch of other microbits listening and orchestrating the motion of the Cyberbot. And so it's pretty much the same approach of saying, well, if in this case, it's a left speed, a right speed, and a number of milliseconds to execute that speed that gets sent. And so what it does is the left speed is still valid, and the right speed is still valid, but the number of milliseconds is changed to a string. Previously, it was a number. Or it gets sent across as a string that can be converted back into a number when it's received. And so this basically crashes the Cyberbot. And if you have students who are remote controlling their Cyberbot in a contest, it adds some impetus for protecting the Cyberbot from the malformed packets and encrypting the data in various robotics contests. And so we start with the just the standard receiver script, and then eventually adding exception handling, again forcing the students to type it in, and then adding encryption and also forcing the students to type it in. And with that, we are just about on the at the top of the hour. So what I would like to do is take a break. It's 6 minutes till, and I'd like to, I'm sorry, it's 3 minutes till. Let's go ahead and resume at 5 minutes past. Welcome back, everyone, to the second half of the Cybersecurity with Python and the Microbit workshop, day 3. What I'd like to do now is just show you a little bit about the artificial intelligence chapter. So this is at learn.parallax.com. And then there's an artificial intelligence link under language. And we'll just look at basic writing microbit programs. And what we're doing is just demonstrating how AI can be used to write scripts, but very much as a double-edged sword. I know I talked about this a little bit on Wednesday. I forget whether it was Monday or Wednesday, but we talked about it a little bit already. And at that time, I jumped to the end and talked about how it was guided through writing a malicious or a script that could be used maliciously, but it was really just a generic script. And so here we have oh, I'm sorry, I'm in the wrong spot. Okay, so what I did was need to get back to artificial intelligence. All right, so artificial intelligence has prerequisites, and I ended up jumping into the prerequisites. So here is, first of all, it just does a general intro of, hey, how do you talk with a chat bot? And it essentially goes into a question and answer session. And if I remember correctly, we basically have a little conversation about how the chat bot can be used, and what is the chat bot, and etc. Now, interestingly, or rather, I wanted to demonstrate something that doesn't work very well. And so here we give it a goal of a schematic and a wiring diagram and have the chatbot draw it. Well, the chatbot did respectably with a text version of the circuit. So here it is in the image, and then here is its text version. Now, going to a different chatbot and asking for a wiring diagram resulted in these messes, none of which are functional. And so that was kind of an interesting introduction to, okay, AI cannot necessarily do everything for you, and you need to pick an AI that's well suited to the application that you're doing. And so that's that activity, kind of an not kind of an introduction, it is an introduction. And then we talk about scripting for the microbit. And so the first discussion is good enough. We ask it to write a script, and it writes a working script. And I'll go ahead and paste this into you so that you can try it out, because it does work. Paste. Now, here we're asking for more features, and what I asked for was a beating heart. And what it gave me was, yeah, a beating heart, but the script is kind of a mess compared to the example that you would find over at python.microbit.org's make it code it section. And so if we paste this one in here, Yeah, it'll work. Send to microbit. So here's the beating heart. That's great. The negative part is that after students have gone through the tutorials, they know that this is really kind of an unnecessarily complex way of doing the beating heart application. And so the next page talks about how to ask the chatbot to refine the script. And this is much closer to existing examples. And what this ends up driving home also is that being able to understand coding will get you a better product from an AI if you're using it as a scripting tool. Now, it didn't really take very much to confound the AI. In this example, and I know I showed you this already, this is the tilt-controlled cyberbot, but what I'd like to direct your attention to is that each display matches, and that the display that or the two displays, the sender and the receiver displays match, and as I tip the microbit in different directions, the microbit tries to point in the direction that if I placed a marble on top of it, it points in the direction that the marble would roll off, indicating that it knows what direction it's being tilted in. So watch carefully and you'll see that the lights on the transmitter microbit follow the direction that I'm tilting it. So can we get the microbit to do it? Well, I'm sorry, can we get the chatbot to do it? First of all, let's try a known working version of this that came from the display tilt direction activity. And so I'll paste you this link, and then I'll paste in the code also. So that's the link to where we are. And then this is the script. And so this is not AI generated. This is human generated and fairly refined. And it's kind of a cool little app that I haven't really seen anywhere else. Probably a number of microbit developers avoid it because it uses the dreaded trigonometry to figure out which way the microbit is being tilted. So if I tilt it to the right, notice that the line is pointing downward and to the right. Now, if I tilt it toward me, again, it's facing down. If I put the edge with the 0, if I tilt it towards the edge with the pad that's labeled 0, the best it can do with the features I'm using are either a little clockwise of 0 or a little bit counterclockwise of 0. But still, it's a decent, it's pretty decent as far as tracking the tilt. Hopefully you guys have this script loaded and are enjoying that too. You guys like that app? Good, good. Yeah, it's kind of a fun one. Now let's take a look at what we get out of the chatbot. So here is the link to AI's first attempt at this chatbot, or I'm sorry, first attempt at the Compass. Go ahead and run it and tell me what you find. So was anybody able to get the chatbot's version of the tilt compass to go? Error, yes. So essentially what happened is when trying to run it, the tilt compass microbit displays a shiny face and displays an error. So back to the drawing boards. So this is the part that guides the student through that. And so as the user, the next thing students see is, hey, chatbot, I got this error. And then we talk about, all right, how can we fix that? And then we actually go to the chatbot and explain to it that there was an error. And so what it does is now it gives us, compared to the original application, kind of a large bloated piece of code. And we talk about iterative development, that we're trying to get something done, it doesn't work, so we try a different approach until it gets done, which is essentially the way new code is developed by humans. And it's the same way with humans with humans assisted by AI. And so after a few rounds, finally, we get to kind of a nice, concise piece of code again. And so this highlights that it's not really feasible to just jump in and ask for something you want. And the moral of the story is that if you don't know your coding that well, don't necessarily expect an AI to be able to code the way you want it to. It's a thing where you're basically going to have to work together in order to get to a piece of code that's actually pretty decent. And so here is the AI's final product. And it's, if I remember correctly, this is a slight improvement over the original because it makes a slight adjustment so that it's not pointing when it gets to 90 degrees, it knows it's between, it knows it's actually between 90 and the next increment above it. And so it calculates, okay, I'm between 90 and the next increment above that. And so it points a little bit more accurately. So the tilt compass is working again, and it's still doing a nice job of displaying generally which direction I'm tilting it. And then we go on to do a script for the Cyberbot. And this is a similar thing where essentially we ask the chatbot to write a script that makes the Cyberbot robot draw a square, and it still takes some hand holding to get it right. And in fact, it makes the mistake that we expect from students of essentially saying, well, gee, if I can make it roll forward and turn right, I can just copy and paste that code 4 times, and that forward and turn right becomes a square. And of course, a little bit more discussion from the AI allows the students to see that they can have it do a better job that's more memory efficient and less verbose and uses the features of Python. But again, you can't really get here without having experience programming Python as a student and having the remembered experience of saying, okay, well, if I made my Cyberbot robot roll forward and turn right once, if I put that in a for loop, I can get that done 4 times without copying and pasting the code 4 times and making unnecessary use of memory, et cetera, et cetera. And so that again is examples of iterative development with AI, and examples of the moral of the story is you, the student, still have to know your coding in order to be able to work with AI to get what you want. We've already looked at that twice. That's the keyboard control. This is the whole Cyberbot tutorial series. This is the one that we peeled away the AI from. So all of the AI lessons are in here, and there's added Cyberbot robot ones, like I mentioned, for the malformed packet attacks and defenses for, as an example. This is I don't know why I put this slide here. What was I planning on talking about? I feel like this slide is oh no, that's right. Okay, so here's the Cyberbot robot, and the microbit has this thing called an edge connector, and it plugs into a board that has a coprocessor underneath. And when the microbit is connected to this board, then the microbit and the Cyberbot robot board can have conversations, and those conversations mostly consist of the microbit telling the Cyberbot board what it wants done with things like servo motor control. That's the motors that make these wheels turn. And then also gathering data from any circuits that are built on here, and also controlling any circuits that are built on here. There's a lot of sensors that come with the Cyberbot robot. And again, this helps really drive home or give another avenue of understanding the lesson of, hey, if you have a piece of code that you want to repeat several times, like going forward and turning to the right, well, you can do that with a for loop instead of copying and pasting the script 4 times. Speaking of the sensors I mentioned just a moment ago that are built on that white breadboard circuit, so the sensors are built typically in this area. The Cyberbot robot has examples, like here is touch sensors, and so it's detecting that it's bumped into objects and picks a new direction. That's of course, the entire thing runs in an endless while loop, but it's also an example of using conditionals. If the whisker is, if a whisker to press is detected, choose a new direction and travel in it. There's also light detection circuits that are used with the Cyberbot robot. There it goes, chasing after the light. Play that again. So no light variation. There's a bright light. Let's go after it. The whisker contact detection is great for introducing a tangible thing that circuits can do and that a script can monitor and respond to. But for real robotic navigation, it's a lot cooler if the robot does not run into the obstacle in order to detect its presence. And so here, those little black tubes sticking out of the Cyberbot robot are little infrared flashlights that are flickering at a certain frequency that the detectors that are also built on that breadboard are capable of detecting the reflected infrared as it bounced off the box and then off the wall in the back. This is just the theory of operation, how the keyboard control works, which is you're essentially typing into the serial monitor. That's going to the microbit via USB. And then you're first prototyping it using a direct USB connection, then making it a distributed app where the data goes to one microbit, it goes out the radio into the receiver microbit, and then the receiver microbit controls the Cyberbot robot. And then tilt control, which we've taken a look at how the tilt is received. We've taken a look at some radio data applications. So that's all old news. I mean, I know that, again, we're really skipping across the surface here, that we've looked at the applications in quite a few different chapters, but have not really delved into the nuts and bolts yet. Our 6 hours is almost up, which kind of goes to show that I really can't go any deeper. That's going to be up to you if you want to try to use this material. Let's see. So that's the tilt controlled Cyberbot. There are more things you can do with it though that are pretty neat. This is one where an add-on of a gripper has been built onto the Cyberbot robot. So here's a little gripper, and it's the same tilt control application to guide the robot to where you want it to go, but the A and B buttons are also added to that data packet, that dictionary that gets transmitted across, and the result is pretty cool. So that's the A and the B button. Hit the A button again. Gripper lifts, and tilt control to back up the Cyberbot, and then guide it to a target, and then use the B button to let go, and then use the tilt control to back away from the object and leave it at a particular spot. Lots of fun. The drive system on the stock Cyberbot is one where you have to kind of trial and error to get it to go straight and to get it to go particular distances. There's some inherent differences in the speeds the wheels go that are related to manufacturing and adjustment. There are servo motors that can be purchased separately that that allow you to write scripts that call out particular distances or speeds, and the microcontroller underneath the Cyberbot robot board is able to take care of the rest. And the way that works is note the little pointer right here. So it's pointing straight down at the table. And this script is set up to make it go in complete wheel turns. It can split the wheel turn into 64 different positions. So note that there it took a full wheel turn forward. And then it turned left and back and right. And then back again, and notice that it's still at the wheel turn. And it ends at the wheel turn. So those are called our feedback 360 servos, high-speed servos, pardon me. And then there's the gripper with feedback 360 servos, which the application on the front page is basically the same idea as one we already looked at. However, there are activities like measuring how far the Cyberbot robot should go. So here we've taken some measurements and then coded that into the Cyberbot, and then the Cyberbot will go and grab one of the cylinders and then place it on this post-it right here on the first try, thanks to measurements and knowing the circumference of the Cyberbot wheel, which means how far will it travel in a particular to get or what number do you have to give it to travel a particular distance? There's also an electronics curriculum with the microbit. It has some pretty cool things that are part of it. I don't know how many of you, I guess I don't have the link for that page. Let's go back to learn.parallax.com. It's called What's a Microcontroller with Python and the Microbit. And it's all about how electronics goes into products and inventions. And it has some interesting features. For example, right here, as we look at this, yeah, this is the animated one. So this is an example of taking voltage measurements. We're using a voltmeter software that's part of our Cyberscope software. It's at cyberscope.parallax.com. And it's designed to communicate with the microbit to take voltage measurements and display them as though it were a physical voltmeter, just like the kind that is used for electrical testing on cars, houses, and electronics benches. And this particular lesson is actually showing, okay, if you take a measurement across this entire circuit, it has 3.26 volts across the entire circuit. And then all the parts are connected to end or in series. And so here with this resistor, we're measuring 1.2 volts. And here with this light emitting diode, we're measuring 2.06 volts. And that adds up to the total across the entire circuit, which again was 3.26 volts. And that's an example of Kirchhoff's voltage law with series, that's parts connected end to end electrical circuits. And students along the way get to measure voltage, resistance, current, and learn about Ohm's law and some of the other things. All hands-on with a very much voltmeter-like setup without having to purchase a sold separately voltmeter. Another important tool in electronics is the oscilloscope. And the oscilloscope this little motor right here is popular in animatronics and in robotics, and it's a servo motor like the ones that drive the robot around, except for it's a standard servo as opposed to a continuous rotation servo that drives the robot around. A standard servo will essentially turn its armature to a given angle. And the way that angle is selected is by sending it brief high signals that if you connected a light circuit to monitor the signal that's going to this this wire and ending up in the servo, what you would see if you could, it flashes 50 times a second. And so there would actually be a flicker since that's faster than human persistence of vision. What we see is that essentially a light would be really dim here, and then it would get slightly less dim, which with each increase in the amount of time the high signal lasts. But what we see in the servo is we see an increase in the angle that the armature turns to and holds. Then, jumping way forward in the example, this is the oscilloscope, and what this does is it measures the amount of time that the actual servo control signal, it essentially graphs the servo control signal for students to monitor, and they can see those different pulse widths, those different durations of that high signal, and they can also see that right next to the servo turning to different positions, as was shown in this little animation right here. And again, there's no additional, oscilloscopes are usually pretty expensive, but this student microbit version of the oscilloscope is no extra charge. It's simply available at cyberscope.parallax.com. And I'm pasting in the link to that just so you can see it. Essentially, there's a little video on the cover slide that shows how the Cyberscope can be used by downloading, in this case, just an example hex file, and then opening it with the microbit editor and loading it in, and then disconnecting the microbit editor. This is the 2.0 version of the editor. We're now in version 3, and going to cyberscope.parallax.com and going through the same connection procedure. I'm going to replay that. So once you get to cyberscope.parallax.com, there's a connect button similar to the 3 dots that we used to connect with the editor. And clicking that connect gives you a list of devices connected, and this is the microbit. And so we're selecting it and hitting connect. And as soon as we do, it starts showing the data. And the oscilloscope has various features, like taking a look at different amounts of time on the screen and then setting what's called a trigger to line up a repeating signal so that it always refreshes itself and the start of the signal aligns with a line that you can move around on the screen, all the same as a normal oscilloscope. And then this is the multimeter feature, and then back to the oscilloscope demonstration. So that's electronics with the microbit. Now back to resources. I want to emphasize that this really is a great warm-up, and there's lots of great things to try here. This is the Make It, Code It page on Microbit's site. So I'll copy that to you guys as a repeat. Another thing about Make It Code It that I want to emphasize is that it can assist in the transition between block code and Python code. So here, for example, is an application that students may have become familiar with in block code. And then here is the block code example. Now they can run it, they can create it with the block code and run it and make sure it works. Then they can try it out with the Python version of the code. So in addition to just being a potential warm-up for Python, it's also supporting a transition between graphical and text-based scripting. Another resource for, so here's an additional resource on top of the Parallax material that we've talked about. Another resource is cyber.org. This is available to United States teachers only. And
hey, Andy.
Yes.
We have a note here in the chat that Andy, your last link didn't paste correctly.
Sorry about that. Let me see. Cyberscope.parallax.com. I click it and there it is.
Not sure there.
The next one you did, Andy, was the make code link. And
oh, it didn't paste at all.
Right. Well, it was the same one.
I forgot to paste it. Oh, okay. Sorry about that. All right, so here is Make It Code It. I'll double check and follow it. There we are. All right, yeah, Make It Code It is a really important site. Either use it as a warm-up or a transition tool or both. In my Microbit for Beginners workshop, which I'll show you how to get there. I'll repeat how to get there in just a little bit. It talks about this. And then also you might notice that there are options for opening in classroom. So you can actually set up a classroom for your students. There's no personal data shared. Every student gets there's no personal data collected, and every student is given a username that is anonymized. And you can see more about that in the Microbit for Beginners, Beginning Teachers class, which I will show you a link in just a couple minutes. So Make It Code It, very important spot. Cyber.org, again, that's available to United States teachers only. And after you join, they have some additional material. Coding Fundamentals is a Microbit. It's got some additional material that might come in handy for some of you on a Microbit introduction. And it does also use both the block code and the Python. You have options of doing either. Then there's Cyber Literacy 1 and 2, which includes some additional material, slides, and etc. for the Cyberbot robot. This is the homepage of learn.parallax.com, and I want to emphasize that this is both the student and teacher portal. So that's the link, and if you follow the link, I lost the link. There it is. Okay, so here's learn.parallax.com. And all of these you can pretty much think about as textbooks and or workbooks for the various things. And of course, we're focused on cybersecurity here. And so here is the cybersecurity, getting ready, dictionary primer, exception handling, strings, things we've looked at. Writing microbit programs, again, this is your most important beginner resource. And I recommend, if you don't know Python, especially working through here yourself, following along just like your students would. Then the teacher portal is, so the student portal is here. It's the home page, and you can use that to get to any of our textbooks. There's also an educators tab. And this is where you can log in to see more. So right now, if you go to, let's say we want to see the cybersecurity with Python and the microbit resources. Well, resources that don't need to be hidden are up front. So for example, here's a link to the microbit editor. Here's a link to where to buy stuff. Here's a link to the learn.parallax.com cybersecurity tutorial series. Here's a link to the Cyberscope I just showed you. That's the, multimeter and oscilloscope. And then here's a link to some of the a playlist of educators courses. I believe this one is for this for the cybersecurity workshop, and the older version of it. Then we have a little write-up on teaching strategy. Again, it's nothing to hide, but once you get to the bottom of the page, this is where the assessment material cannot be reached until you sign in. And signing in is simply going to educators and following the login link. So then it'll ask you to log in. Well, I logged in on a different browser. So here I am. So this is before login. So imagine me typing my credentials in here and then clicking the login button. And then this is after login. Now going back to educators and then opening cybersecurity with Python and scrolling to the bottom, lo and behold, instead of a giant lock and a message saying, if you need to sign up by emailing us and proving that you're a teacher, which is normally just done by using your teacher email address. And then we can look you up in the staff directory, and usually that's a done is done kind of thing, and we add you to the list. So here is the assessment material. And then there are various zip files. So I guess we'll take a look at, let's try encryption intro. So there's the zip file. And then we'll take a look at it in the folder, which opened up on another screen and dropped behind my Zoom window, which is rather persistent. So here is the downloaded zip. And we'll go ahead and unzip that. Extract. And then here is the extracted files, which you get a PDF and a PDF and a Word doc. And then it looks like in this case, there's a PDF answer key. So I'll open up the PDF, then go back. So that's the handout. And then here is the answer key. Both of these are PDFs. So here's the student worksheet for encryption. Oh, so here's the student worksheet along with the answer key. So be careful to note at what point you have your red teacher solutions because you'd only want to print in this case through page 3 on this particular handout. And then the assessment material is here for you to use later. And then and I'm not sure exactly what this is. I probably shouldn't have randomly grabbed one of these. I believe it's a solution to one of the your turn try this activities that that is not solved on the web page. So that's an example of going in and grabbing the assessment material from the learn.parallax.com website using the login that you either just got between Wednesday and today, or that you've had and you made sure to dust it off and try to log in. So now you can get to all this material. So that's the educator slide. Buying microbits, you can, we are one of the official microbit sources. And so I'll go ahead and share you a link to parallax.com shop microbit. Where is it? There it is. Okay, so this is all things microbit, and you can refine that. For example, you can look at just the kits. And then here's the 10-pack, the microbit club bundle, and then further down is the microbit go bundle. We sent you 2 of these to use to attend the workshop. But I'll back out and just do the all things microbit page and paste that to you. And we also have the Cyberbot robot page, which, or well, the Cyberbot robot appears in the unfiltered, or okay. So I should have said that you go to www.parallax.com instead of learn.parallax.com if you want to buy microbit modules. Learn.parallax.com is just student workbooks and teacher resources. Now, www.parallax.com, when you go here, you can click shop, and then you get to your microbit category, which I just pasted in, and that's where you can see and buy all things microbit from Parallax. Little blurb about upcoming workshops, and then I also mentioned that I would show you again a repeat of the microbit for beginners. So I'm going to start, well, upcoming workshops. First of all, I want to point out that we have a new event. It's scheduled for May 21st at 3 p.m. Pacific. And this is where you can come and talk with the Parallax's leadership and Parallax's educators to learn new stuff, like get some tips and tricks from us. And then you can also ask questions of us. And this is an open format thing. This is nothing like the last 3 2-hour sessions of the workshop. This is an open forum for educators and Parallax education to basically better serve you. And so we'd like to invite you to this. And I highly recommend signing up and joining us there with a grocery list of questions and comments at the ready. Now, going back to the events, and that's community events on the www.parallax.com page. Let's see, and I did paste in this Parallax EDU chat. And then we have some in-person, if any of you are going to, say, NICE K-12, Ignite ND, cyber.org's EdCon, Utah has a CTE. Anyway, there's lots of in-person workshops and conferences that we're going to be at, and you can come and meet us in person there. I mentioned that I demonstrated in another workshop how to use the microbit classroom. And that is this microbit for beginners. These are all previous workshops. So you could, for example, attend the Cyberbot workshop in a self-guided style with access to all 3 2-hour videos and the slideshow for that, and get up to speed with the Cyberbot. There's also the microbit for beginners, and especially for teachers who are new to the microbit, new to Python programming, and potentially if you're interested in using graphical programming. We talk a lot more about graphical programming here in this event. And this is where, again, I highlight the use of the Make It Code It site, and also near the end, I think we did a demonstration of the microbit classroom. And so that link is coming at you. It's a single 2-hour YouTube video. And when you follow the YouTube link, the chat log is actually in the more info section of the YouTube video. So all you have to do is click more here below the video. I'll just kind of go to a particular spot. So here we are talking about the graphical programming language. But if you click more in the description below, there's the entire chat log. Of course, all of our teacher attendees have been anonymized, but Ari and I, it calls out when we paste in things, and then all the attendees are just labeled attendee. And that pretty much wraps it up. Here is all the different ways to get a hold of Parallax. Specifically, the Educator Hotline is open from, it's behind my camera. The Educator Hotline is open during normal business hours, California time. You can contact us through it. You'll get to our sales department, and then depending on what kind of assistance you need, they may refer you to me or Ari or Stephanie. There's also education@parallax.com. This is the most recommended way to reach out to us, because this goes to the entire education group, and then the person best suited to answer the question is chosen and assigned to you to answer the question for you. Then there's a direct sales line for requesting quotes and submitting purchase orders and all that stuff. We also have discussion forums, a presence on Facebook, YouTube, and etc. And all of those, by the way, all of our social media presences are at the very bottom of www.parallax.com. So Facebook, X formerly known as Twitter, YouTube, and etc. So it's 5 o'clock in California. They say it's 5 o'clock sometime. Well, it's 5 o'clock here in California, and the top of the hour, the end of the 2 hours, and the end of the last day of the workshop. I'd really like to thank you all for coming. It's I think it was a really productive session, and please do go ahead and email education@parallax.com if you have any follow-up questions. And then remember that there's also that upcoming educator informal chat I'll paste that in again as the very final link on here. So we'll hope to see you with that. And if not there, at some point in the future, if we can help you out with anything, please feel free to reach out to us. And also that concludes the recorded portion of this workshop, but we'll be happy to stick around for to answer any questions you might have before you start your weekend. Have a great weekend, everybody, and I'll look forward to seeing you again sometime not too long from now.